Yeah. So last week we don't have a class, yeah, through Zoom, but I have uploaded some videos for you to watch, yeah, so that I expect that you have seen the video. Have you?
Yes, ma'am. Yeah.
Okay. What about the others?
Yes, ma'am.
Excuse me, ma'am.
Yes.
May I ask a question from the video, ma'am?
Yes, of course. Yeah, Fifi.
In slide 30, I still confused how we get f power for x equals to minus 2400.
Which one is that?
Slide 30 about Simpson 1/3 rule.
Okay, the Simpson 1/3 rule. I will check again because the number of the slides here is not the same. About finding the error, yeah? Is it?
Yes, ma'am.
Okay, so it's about finding the error of the Simpson 1/3 rule. Okay. So that should be I will try to share the slide here. Okay, is this the slide that you mean?
Yes, ma'am, but the example one.
Example one. Oh, the example here. Here.
Yes.
Okay. Okay, so the question is about the Simpson 1/3 rule, yeah? So the third method here, yeah?
Yes, ma'am.
Okay, so here to find the value of the fourth derivative, yeah? To find the value of the fourth derivative, it means that we have to find the derivative of the equations, yeah, the fourth derivative of the equations. So that if we look at here, we have these equations, yeah. So that we can find the first derivative, yeah. So that will be 25 minus 400, yeah. So I will try to write it down here. So if we calculate f1x, the first derivative of x of the function, yeah, so that will be 25 minus 400x plus 675 times 2, yeah, so that times 2 times 3 squared x minus 900 times 4, that will be 3600 x to the power of 3 plus that will be 2 0 0 x to the power of 4, yeah. So that when we find the second derivative, so that will be minus 400 plus, so this is multiplied by 2, so that will be 1350 times 3, so that will be 4050, so this is correct, minus that will be 10,800 squared x plus 8,000 x to the power of 4, yeah, so that will be 8,000 x to the power of 3. Okay, so this is correct. And then to find the value here, so we can do the integration from between the limits from 0 to 0.8, and we integrate it to dx. Yeah, and then we divide it into with 0.8 minus 0. So that if we want to find for the third derivative, so we will calculate the third derivative here. Yeah, so that will be equals to 450. Yeah, 450 minus that will be 21.6. Yeah, x plus that will be 24,000. Yeah, 24,000 squared x. So that the fourth derivative will be minus 21,600. Yeah, plus 48,000 of x. Yeah, and then we do the same thing as this one. So we can find the average of the fourth derivative in the interval. Yeah, so that will be from 0 up to 0.8, where the function is minus 21,600 plus 48,000 x, and we do the integration up to dx, and this is divided by 0.8 minus 0. So with this, if we do the integration, so that will be minus 21,600 x. Yeah, back again to the value before. Yeah, so that is minus 21,600 x plus 24,000 x squared, and this is from the limit between 0 up to 0.8. So if we insert this value of 0.8, so then we have 2160 times 8. Yeah, so if we insert that 0.8, can you help with the calculation? So that is multiplied by 8. Yeah, 4, so that will be 48, 8 to 12. Yeah, minus 3,240 plus we have here times 0.8, so that will be 22,400 times 8, so that will be 2 times 8 is 16, so that will be 19,200. We multiplied again with 0.8. Yeah, so multiplied with 8, so that will be 619 times 8, 72, 73, 7, 15, 360. Now that is minus 3,240. So that will be 20. And that will be 1. That will be 12. Yeah. So that should be divided by 0.8. Yeah. Is it? So that should be divided by 0.8. What is it? So that is should be 12. So the value is not the same, yeah?
Yeah, it's not same.
Yeah, it should be 12,120 divided by 0.8, isn't it? Now you can check that again. So what about this one? Have you tested with this one? Is it correct?
I have not, ma'am.
Okay. Okay. I will check again. Yeah. I will check again to make sure that, yeah, if there is a mistake in the calculation, so this value should be corrected. Yeah. So this value should be corrected. But in general, that is how to calculate for the value. So this one as well, yeah. So this one, multiple application. The fourth derivative is also similar as well. And this one is also similar as well. So we will try again. Yeah, I will check again. Yeah, to make sure that this calculation is correct, but it's due several times. Yeah, so I will check it again. Yeah, and see whether this is incorrect. So I will let you know again, inshallah. Yeah. So I need to check the value first, but it should be calculated like this one. Yes, because we want to find the average of the fourth derivative in the interval. So that will be the same formula in calculating this, yeah. But we have to find the fourth derivative first, and then we do the average by doing the integration and then divide it with the interval length. Yeah, it should be like this. But yeah, I will check again why the value is not similar to the calculation. Yeah. So I will check that again. Okay, I will make note on that.
Excuse me, ma'am.
Yes.
I want to ask about I still confused about the difference between f derivative with f bar derivative. What is the difference, ma'am?
Okay.
And the calculation, why the calculation is include the integral there? I still doesn't know about that.
Yeah, okay. So here is a calculation of the approximation of the error. If we don't have the true value, yeah. So in this case, we have the true value, so that we can directly calculate the true error. But in some case, we don't have the true value. So in that case, we can approximate the error with this value, yeah. So that will be minus 112 times the average of the second derivatives multiplied by p minus a to the power of 3. Yeah. So this is an approximation for the error. Yeah. So when we want to calculate the order of the error, yeah, when we want to calculate the order of the error, so that we can calculate by we can approximate with this value, and the difference between the second derivatives here with the sign with bar here. So bar here means average, mean, yeah, the mean value. So that if we want to find the mean value, yeah, so that we can find it by finding the integration of the function. Yeah, so that will be the area underneath this curve, for example. So this is the curve, this is the equations for the second derivative. So this means that this is the curve for the second derivative. So to find the average, we can do the integration and then divide it with the interval length. Yeah, with the interval length. So this is the difference. So with bar sign here, it means that this is the average. Yeah. Okay. So yeah. Yeah, so that is to answer your question, Sultan. Yeah.
Oh, okay, ma'am. It's very, very clear, ma'am. Thank you, ma'am.
Thank you too, ma'am.
Okay, for Fifi, I will check again, yeah, for the calculation to make sure that, to calculate again the correct value. If not, so that should be corrected. Yeah, thank you. Okay,
thank you, ma'am.
Yes. And what about the others? Any questions on this? So all of you have seen the video, yeah?
Yes, ma'am.
Okay, so no question on that. Okay, if there is no question, so I will continue to another method of integration. And this method is actually based on the previous method that we have learned. So in summary, what we have learned from the videos is that we have basically three methods. Yeah. So the first method is the trapezoidal rule, in which we approximate the area underneath the curve with a trapezium shape, yeah. And then we have Simpson-Walter rule, in which we approximate the function, the real function, with the quadratic equation so that we can find the area under the quadratic equations. And with Simpson-Walter Simpson 3-8 rule, it means that we approximate the real function with the third order equation or cubical equation so that we can find the area underneath. And we can also apply the multiple segments for each of the method that has been discussed. Yeah. So using any of these, we can apply multiple segment. And please be careful that because Simpson-Walter rule here requires at least 2 segments to obtain the equation. So that means that if we want to apply the multiple segment for the Simpson-Walter rule, so that there is a special requirement. Yeah, so that the requirement is that can only be used. Yeah, if we want to use that with multiple applications, so multiple segment, so this can be used only with even number of segments. Yeah, only using even number of segments. So, for example, if you have 9 segments, so it means it's not possible applying the same segment with multiple Simpson-Walter rule. Yeah, so that we have to combine with other method as well. Okay, so this is about the 3 methods that we discussed. Now we will go on chapter 22, which is about the integration of equations still, but we will talk about one method here, which is a further improvement for the trapezoidal rule. So we have seen before that the trapezoidal rule is very simple, but the level of the accuracy is quite low because it's only using a linear line or a trapezium shape. So that we want to increase the accuracy of the trapezoidal rule. Yeah, so we see here that if we have a trapezoidal rule, so that we have a with a subinterval h, that will give an error of the order of h squared. Yeah, so this is an error. So that if, for example, we want to increase to higher order scheme, so that we can combine 2 trapezoid, yeah, which is estimated at the interval h and half of h to get a better estimate. So what does that mean? For example, we have a calculation, yeah, with delta h. For example, we have a function like this one, in which we have fx and x here, and then we want to integrate from a to b. Yeah, when we want to integrate from a to b, so that here we can apply multiple segment. For example, here now, say we use 3 segment like this one, in which for each of the segment here we have h. Yeah, the interval length for each of the segment is h. So that with this we have the calculation of I, which is this one is called I h1, in its h1 here is equals to h. So we have the calculation of the error, so that will be I1 plus I2 plus I3. Yeah, so that will be the total. So if we have, for example, we have 1, 2, 3 segments, so that the total integration area with the length of the segment of h1, which is equals to h, so that will be equals to I1, I2, and I3. And then we do the second calculation, which is the integration with the length size of h2. And the length size of h2 here is half of the initial length that we use. So if we use previously h1 is equals to h, now h2 is equals to half of it, so half the size of it. So that it means we now use the segment which is twice of the initial. Yeah, so previously we have 3 segments. Now when we use the interval length is half of it, so it means that we have more segment. Now we have twice of the segment of the previous, so that we have I1 plus I2 plus I3 plus I4 plus I5 up to I6. So twice the size of that one. Yes, twice the calculation of the previous one. So that if you look at each of these, yeah, so the difference is only the number of segments. So it means that the order of the scheme is similar. Yeah, it's still lower order scheme, but we're applying at different number of segment. Now to get a higher order scheme, so that we can combine this one, so this two lower order scheme, such as this one. Yeah, so we calculate the new integration that will be approximated by 4/3 of the integration area calculated with the interval length of the segment of H2 and minus 1/3 of the integration area, which is calculated with the interval length of the segment is equal to H1. Yeah, so it means that we combine the last segment, the calculation of the integration with less segment, and the integration of the calculation with more segments. So we combine both, and then when we do this calculation, so that we have a higher order scheme. Yeah. So this is basically the calculation. Yeah. So that if we want to obtain the higher order accurate scheme, so that we combining each of the calculation for the integration area with different H value. Yeah, so that we can construct a table like this one, in which the first one here is we see here that we have R00. So the first here, yeah. So the first here is denotes that this is the number of segment that is used. Yeah. So this is the number of segment that is used. So that, for example, we have 0, 0 here, R00. It means that this will be 0, n is 0. Yeah. So that will be 1. Yeah. So 2 to the power of 0, that will be 1. So it means that that will be only a single application of the trapezoidal rule. And if we use n is equals to 1, it means that we use 2 segments. Yeah, so this is only 1 segment or a single segment. 1 segment, sorry. So we have only 1 segment. And then we have the calculation here of 2 segments. And then we have here 3. Twice of it, so that will be 4, and this will be 8 segment. Yeah, so that we calculate the integration area with different number of segment, and then afterwards we can calculate the higher order scheme. Yeah, we can calculate a higher order scheme by combining the value, yeah, between the less segment with the more segment. So the result here will be of higher order. So this is the calculation derived from. Yeah, so that if we look at here, so that if we want to have higher order scheme, in which we have previously where we have the first order, the second order error here, which is for the trapezoidal rule. So that combining these two methods here, so we end up with a higher order scheme, which is the error level now becomes 4th order. Yeah, 4th order. So how to combine that? So that we combine the new integrated area will be 4/3 of IH2. So this is IH2 minus 1/3 of IH1. Yeah, so this is what is performed in the Romberg method. So we simply combine together, yeah, the value from the lower order scheme with different number of segments, and then we will obtain the higher order segment. Again, we can combine as well here. For example, we want to use, here is 2 number of segment, and then we want to compare with 4 number of segment, for example, here. Yeah. So that here we can find the new value, yeah, which is R21. So R21 will be 4/3 of R20 minus 1/3 of R10. Yeah. So that will be the higher order integration value, yeah, with more number of segments. And then if we want to increase further to 6th order accurate, so that we combine the value here, R21 and R11. Now, how to combine that? Because now we want to get to a higher order, So not the same to the fourth order, so that the equation will be different. So when we calculate R22 here, so that will be equals to, so this is a correction, yeah? So this should be 16 over 15. So please correct that, yeah? As well as in the book, yeah? So this should be 16 over 15 IM minus 1 over 15 IL. So which one is IM and IL? So IM here is the number, the value which using more, yeah, more segment minus 1/15 of the integration using less segment, yeah. So that if you calculate this one, so that the value of R22, that will be equals to 16 over 15 IMM, which is R21, R21 minus 1 over 15 R11. Yeah, so this will be the calculation. Again, if you want to increase to higher order, so that we have a 0, the order will be of the eighth order, yeah, the error will be eighth order, so that we can combine this value, yeah, together. So that to calculate the new area, so that will be 64 over 63 times the integrated area of more segment, which is R32, minus 1 over 63 of I using less number of segment. So that will be R22. Yeah. Okay, so this is how to get a more accurate result, yeah, to the higher order level. Okay, so we will try here. Okay, so for example, we have this graph. We have x squared, yeah, in which this is 0 and 1, for example, like that one. Okay. And then we have positive, so probably like that, yeah, the curve. So like that, so that we have fx and x, yeah. So if we have this graph and we want to do the integration here, yeah, so this will be the integrated area. So that now the first step is to use h is equals to 1. So directly b minus a, so only 1. So one segment. So then we do the calculation of the triangle here, or the trapezium here, or similar to triangle in this curve. So that will be half of 0 plus 1. Yeah. So that the result will be 0.5. And then we divide it into two segments. So this is the first segment, I1, and this is the second segment, I2. So that when we have h now, the step size or the interface size now becomes half of h, half of the initial here. So then when we do the calculation, so that we have the calculation of the first area and the second area, so that will be 3/8. So this is the value. So that how to calculate this one? So the new area here will be, again, we look at the equation, that will be 4/3 I with more segment minus 1/3 of I with less segment. Yeah. So that we continue here, we see that it will be 4/3 of the value which has more segment. So the integration area with more segment is this one, minus 1/3 of the integration area with less segment. Yeah, so that we have here, so that will be, what is the value here? So that will be half minus so that will be 4/3 times 3/8 minus 1/3 times half. Yeah. Okay, so this is correct already. So that when we multiply that, so that will be 1/3 of half. Yeah, so that will be 1 times half, so that will be 2. So that will be 1/3. Yeah, correct. So that will be 1/3. Okay, so this is how to calculate the integration area. Yeah, so it means that when we have this value, so this is the integration area. So this is at the order, the order of h to the power of 4. So fourth order error. Yeah, fourth order error. So this is the Romberg method. So we can increase the order of the accuracy, yeah, the order of the accuracy by combining two method, yeah, which is the trapezoidal method, to integration using lower order accurate scheme. Yeah. And then again, we can further obtain. So this is h to the 4 square. Yeah. So second order. Sorry, this is second order. So this is fourth order, and we can extend to sixth order. Yeah. So when we want to extend to sixth order, it means that we have to find the area using more segment. Yeah. So that if we previously calculated with one half, so that for this one, this should be calculated with h is a quarter. Yeah. So twice of that. So this is one segment, this is two segments, and this is four segments. So with four segments, we have h now divided by 4. So that now we calculate the result. So that will be 11 over 32, yeah, with multiple trapezoidal rules. So this is the value. So once we have this value, so that we can calculate now this value, yeah, in which the higher order value combining 4 segment and 2 segments. So that will be 4 thirds times 11 over 32 minus 1/3 times 3 over 8. Yeah. So that we want to calculate the value here. So that with this one, this will be 8. Yeah, is that correct? Yeah, correct. So that we have here will be the same. So that we have 11 minus 3. So 11 minus 3 is 8. So 8 over 8 is 1. So that we have 1/3. So this is correct. Yeah, 1/3. So we obtain the fourth order error, yeah, for this calculation, and we see already that the value is the same, either using by combining the 2 segment and 1 segment, or when we combining 4 segment and 2 segments. So this means that this is actually is already the same result. Yeah, but we can further increase it to 6th order. So if we want to use the 6th order equations, so that we combining this IM with IL, yeah. So the calculation here will be equals to 16 over 15 of the value here. Yeah. So IM is 1/3, which is the bottom, more segment, minus 1 over 15 times 1/3 as well, because the value is the same, 1/3. So that the value will be constant, 1/3. Yeah. So with this, we have, this will be the result for the 6th order accurate or 6th order error. Okay, so this is a Romberg method. Yeah. Any question?
Not yet, ma'am.
Not yet, ma'am.
All right. Okay. So yeah. So with that, we can continue a bit on Gauss quadrature. Yeah. Gauss quadrature is another method in which we adjust the position, yeah, of the line. Yeah. So the points that is used to create the line is now adjusted. Yeah. So that here we have a strategy, yeah, of positioning any 2 points Okay, so with Gauss quadrature, we put a new points. Yeah, so we use 2 points on a curve to define a straight line that would balance the positive and negative error, so that the area under the straight line will have a better estimation for the integral. Yeah, so this is basically still using trapezoidal rule. Yeah, still using trapezoidal rule, but the points that is used, yeah, it's not the point that we use as a limit, yeah, from A to B. So that we see here that, for example, we have A here, the trapezoidal that we learned before, yeah, in which if we want to integrate from A to B, so that we use the point of A and B directly to get the linear line. Yeah, so with Gauss quadrature here, we don't use the value of the limit here as the point to obtain the linear line, but we choose another point inside, yeah, another 2 points inside, in which this will balances the positive and negative difference. Yeah, so for example, if we have, this is the limit of A and B, so this is the value, we don't connect that directly, but we choose another point here inside in which this will balance. Yeah, so we know that this will be of underestimate the area in this region, but here it will be yeah, so this will be overestimated and this one will be underestimated. So the total area, when we calculate that one, the difference here, so that will be approaching to the real value. Yeah, that will be approaching to the real value. So this is what perform in Gauss quadrature. So that it means that we have to find a new point, yeah, a new point inside the area, yeah, which is x0 and x1. Yeah, so it's not the limit again, yeah, to get the linear line, but we use another points. Yeah, we have another 2 points. So that when we replace the integration here with a function, yeah, in which now this function using 2 other points, so that we have several unknowns here. And the main important solve for the unknowns here is to make. Okay, so this is the basic of Gauss quadrature. But for this course, this will not be discussed in detail. Yeah, this will not be discussed in detail. So that in this case, for the integration for this course, yeah, so that the integration area, yeah, will be 4 methods. Yeah, so there will be 4 methods that is discussed in this course. Yeah, so we have trapezoidal. Yeah, we have trapezoidal, and then we have Simpson 1/3 rule, and we have 3/8 rule. And last is the Romberg method. Yeah, so these 4 are the main topic that is discussed in detail, while Gauss quadrature will not discuss in detail. Yeah, so I suppose that will not be included in the exam as well. Yeah, okay. So this is for integration. All right, any question? Okay, so I hope that is clear enough, yeah? So that with this discussion lasts about Romberg method, so that will be the method, yeah, that we have discussed. Now we will continue to differentiation, yeah. Now, before we just finish integration, now we also have differentiation. And when we talk about differentiation, we have learned about that as well when we learned about Taylor series expansion, yeah? So remember? So that I will open the slide here. Okay, so now we continue on chapter 23, which is still in the same part, which is about numerical differentiation. Yeah, and we have learned of this before when we learned about Taylor series expansion. Yeah, so we will just do a quick review on that. Yeah, so this will not be long. Just to remind you that we have learned of this, and there are several schemes that are available. Yeah, there are several schemes that are available. Still, I think you still remember on this. Oh, why it's not working? All right. Okay, so you remember that we have the Taylor series expansion, yeah, in which we can approximate the value of fx1, fxi plus 1, in which we can approximate the value of fxi plus 1, that will be equals to fxi plus f accent xi times h plus squared h over 2 factorial second derivative of xi plus and so on. Yeah, and then we can do truncation for this. Yeah, and the order of the equations will depends on how many terms that will be included in the formula. Yeah, so if you use less term, for example, like this one, we approximate fxi plus 1, that will be equals to fxi directly. Yeah, so this means zeroth order. Yeah, zeroth order approximation. If we use two terms, or that we use a linear line, so in this case we have the first order, and so on. Yeah, so it depends on the number of terms that is included in the calculation. So that we can also do the expansion backward. So that we have learned before that we have several methods, depends on which in which direction the expansion of the Taylor series is performed. Yeah, so that we can have the forward scheme. Yeah, so I think you still remember we have forward, backward, and central difference. Yeah, and we can use that to find, for example, the first derivative, the second derivative, the third derivative, and the fourth derivative. And also we have the order of accuracy. Yeah, so it means that we can have the selection of the scheme, which is forward, yeah, backward, or central. And we can find this to find, for example, the derivative. Yeah, the derivative can be first derivative, which is fx and x, or the second derivative, which is second derivative like this one, or the third, and so on, up to the nth order derivative. Yeah, and we can also have the order of the accuracy. Yeah, the order of the accuracy, regardless of the chosen scheme and derivative that we want to find. The level of accuracy here is also needs to be determined, whether we want to use the first order's accurate scheme, the second order, or higher order, for example, third or fourth order scheme. Yeah. Okay, so I think we have seen that example before. Yeah, is it correct? We have learned about this before.
Yes, ma'am.
Okay, so that we will do that quickly. And why we repeat this, yeah, because we will later talk about ordinary differential equation, in which we will use again the numerical differentiation. Okay, so because we have learned this, so I will just do this quickly, yeah, as a review. So that if we want to use backward difference, it means that the derivative will be calculated by connecting that point with the point before. So moving backward, yeah, connecting to the point backward. So xi here, all of the value, the derivative at xi here is calculated by connecting that point with the point before. So that with xi minus 1 or xi minus 2 and so on. Yeah. Or we can also have the forward scheme. Yeah. So this is the derivation. I think we have also discussed this as well. Yeah. Correct?
Yes, ma'am.
Yeah. Okay.
Yes,
We
ma'am.
have discussed. Yeah. We have discussed this as well. So we can skip on that. So for the second derivative as well, we can also combine the equation. Yeah. For example, we have fxi minus 2 and we combine the Taylor series expansion to fxi minus 1. When we combine both equations, so that we end up with a new equation here to find the second derivative, in which this is also first order, because when we divide it with h squared, so this will be h to the power of 1. So this is first order accurate to find the second derivative. So this is called, this is how to calculate the second derivative using the backward scheme, because we use all points before xi. Yeah, backward scheme, which is the order of the accuracy is first order. Aside from that, we have another method now, which is the forward approach. So that it means, again, similar to before, we can find the first, the second, or the third derivative at xi. Yeah. So the point is finding the properties or the derivative at xi, but by connecting it to the point forward. Yeah, the point in front of it. So that now all of the calculation or the formula here using the points after. So I plus 1, I plus 2, I plus 3. So this is forward difference. And we can see here that with this derivation, from this derivation, we can see it clearly that the resulting in this case is first order. Yeah, with using this formula. And the third scheme is the central difference, in which we can find the first, the second, the third, and so on derivative. Yeah, by if we want to find the value at xi, so the value here is found by connecting the point before and after. So you see here that we have xi plus 1, xi minus 1. Yeah, xi plus 1, xi, and xi minus 1. Yeah, so we have connecting the points backward and forward together. Yeah. And how is the derivation? We can find the derivation or the steps to get this formula by combining two equations of forward and backward. Yeah, the Taylor expansion backward and forward. We combine together, we do subtraction, so that we have the result here. Yeah, the result here will be of h squared. Yeah. So it means that this is second order error. Yeah. So with central difference, we see here that the lowest accuracy will be second order. Yeah. While for the forward scheme and backward scheme, the lowest accuracy is the first order. Yeah. Okay. So this is the difference.